All right. Baker, 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 Baker. Get that guy's phone number and let's get on with life here. All right. Kinematic indeterminacy. Basically a fancy way to say how to find out how many equations you're going to have. Hunter, what's it a easy way of saying?
Sorry, I was talking.
Oh, I love seating charts. They're great. They really are. Kinematic indeterminacy. A fancy way of saying how do you find out how many unknowns you're going to have with a stiffness method. In this case, with slope deflection equations. You simply count how many things you don't know. How many things on this one do you not know? How many thetas, how many deltas, how many? Alahar? 3. Okay. Dietz?
4.
All right. Crawford's not here, so no sense in asking him. Wheat's not here. Gonzalez is here. Gonzalez, how many things do you not know? In other words, let's say that I put a load on there, and I want you to solve for the end moments, and therefore get me a shear in a moment diagram by slope deflection method. How many thetas, how many deltas do you not know? I got a 3, I got a 4. 4, oh, that's 2. Morrison? Yes, okay, that's a good guess. Yes. None. You know everything. You say, well, if I know everything, how can I get answers? Well, you simply look in the front inside cover on the first page, and the answer for all the moments are given in case 2. Nothing's unknown. Fixed end moments, we already know fixed end moments. If worse came to worse and we had a weird case that we didn't know the fixed end moments in a span, we would have to, well, I guess we'd have to go ahead and use flexibility methods to get the answer and write it down inside the cover. There are no unknown thetas and there are no unknown relative end displacements, and that's what this method calls for, and that's what any stiffness method calls for. Booth? Well, here, let me say none. Booth, how many unknowns? 1 is probably what most people would say. I was thinking that you might go ahead and say 2, and then when you'd say, well, but wait a minute, I think we've been deciding to exclude axial distortions in our solutions, then we're back to 1. I agree. 1 degree. Love? Love here today? Not many people here today, are there? Williams, holler at me if you're here. Williams? Morrison? Garza? Where's Garza? Oh, hello, Garza. Mayhem? And Condon's here, and Keith Kleinenberg is not here. 1, 2, 3, 4. 1, 2, 3, 4. Where do I run out of people? Morales?
Yes,
Your buddies are the ones not here. And Megali. And Maley. Dismute. Kuntz. G. Green. And Green. And Marino. And Harris. And where's Lane? My brother's keeper. Van Schmidt's here, and they got about 5 people on the back row. That's a pretty good showing on that side. Getman, give me a break. Bourne, everybody else is here. Lane, Marshall, Adams is here. Oh, I'm sorry. You're the broken seat guy. Adams, although you always have a vacant seat, don't you? And Plummer's not here, and Clopton's not here, and Cooper's. Hello, Davis. Thank you for coming.
You did hear me say I'm close, right?
And King is not here. I'm sorry. What's that?
Clopton is here.
Clopton is here? Oh, I'm sorry. I thought you were Marshall.
Negative. I just like to float up and down with you guys.
I see. All right. So we got Booth and all of his buddies. Yes, sir. Okay. Okay, there we go. Ward's not here. She's gone. She quit. What a weenie. Bustamante. Sortiman's here. Dopkin. Winfield. Winfield, where's Winfield? Oh, I'm on the wrong row. Emirage. Does anybody know what Emirage looks like? And Panabecker. And Love. And Johnson. This is pathetic. Galvin. And Roberts. Thank you, Roberts. And Leon. And Serrata. All right. They'll probably come dragging in. Which one is that? Adams?
Yes.
All right. Okay. How many degrees of indeterminacy now? Pick somebody at random here. Adams. Yes, you are. Stroup. This one had 1. How many does this one have? It still has 1. That's correct. There's 1 degree of indeterminacy by a stiffness method. All right. We'll start right here. How many? Here we go. A volunteer. That's too late. You bought it. The guy says going, and you now have a song from a famous professor, and you paid $2,000 for it. Why is there only 1? Because there's only 1 rotation here that you don't know. There's a theta on end B. Now, if the rest of you say, oh, I didn't see that, if he's the only one that's got the guts to say, we don't understand, I think you understand. So holler. And it didn't move up and down, so there's no delta relative to the 2 ends. And there's definitely no elongation because it's pinned. But it turns out if you omit axial deformations, it's still 1 unknown theta at B. All right, we're back to 1. All right. Does this joint have a rotation? No? Well, not if there's only 1. But if you loaded it up, could this joint rotate? Say yes. Very good. It could. And could this joint rotate? And say yes. That's right. And can this joint rotate? And say yes. Oh, you sucker. And the answer on that one is no. Okay? Yes, sir?
Is that first joint that you circled, is that a pin or is that fixed?
This thing right here Are you talking about this one?
Yeah, I didn't know if it was pinned or if that was fixed.
No. Fixed, comes in without the little triangle.
I didn't see the triangle.
Okay. Well, I don't doubt it. They're not real big, but for $60,000 per degree, you only get so much paper and so much pencil. That's it. All right. Now, what else about this one? Yes, Booth. It moves horizontally. And excluding axial deformations, this point here would move the same amount as this point here would move. So we would just have one more unknown, and it would be a delta. The theta at A, and the theta at B, and the theta at C would go into those slots in your slope deflection equations, and your delta would influence how many members. In other words, when you wrote down your slope deflection equations for this case right here, how many times would delta appear? 4 times. In other words, it would look like this. So there would be a delta at B looking back at A, and there'd be a delta at A looking at it from B, and this would be the same number, but it would appear in the equation for delta C to D and delta D to C. And all 4 of them would be the same number. There'd be just one delta involved in the equations once you got them all written down. All right. Remind me to get this thing back to a reasonable size. Green. Look at them looking at each other. Green on the right, not my right, your right. Green, how many unknowns? Okay, I'm going to count them. 1, 2. Would you like to revise your number? 7. Now you're talking. 4, 5, 6, 7, 8. That's correct. There'd be a delta. If this is A, B, C, D, E, F, G, H, I, there would be a delta at I looking back towards H, and there would be a delta at H looking up towards I. And that would occur in all of these members. And then at point H, there'd be a delta, and that would be a delta at H looking back towards G, and a delta at G looking back towards H. And of course, these are relative displacements. So if anybody asks you how far did this point move to the right, you'd be solving for this number and for this number. This guy just goes along for the ride with this one. All right. Baker, how about this guy? One, 2, 3. Would you like to revise your answer? 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that's right. And of course, those joints don't stay square. They, of course, rotate. So there would be 4 and 4 is 8 plus 1 is 9. Okay. McMahon. Not here? Oh, I thought I saw his. Oh, thank you. Where's McMahon? Okay. How many? 2 is correct. 1, 2, and 3 not fiddled with. 1, 2, and no chance of number 3, delta. 1, 2, 3. The deflection on that end, the same as the deflection on that end. 1, 2. No movement, no movement. 1. All right, let's try this then. This is unknowns. Thank you. This is number of unknowns by flexibility. This is stiffness. Number of unknowns. Now the stiffness methods, there are a bunch of them. Moment distribution, conjugate, I don't remember conjugate beam, there's just all kinds of them that they work nice. But once you know one of them, you're good to go on any of them. Flexibility has just pretty much one way of doing business, but it has a whole great big range of possible released structures. So here is the structure. Oops. How many unknowns using a flexibility method? Flexibility method is where you take off enough external or internal supports. Hunter? I haven't asked the question yet. Well, you're really anxious there, huh? Flexibility methods are where you release enough internal and external results to make the structure into a statically determinate structure, realize it doesn't fit, and then come back in with what they call a complementary solution and make all of those distortions go away, all of the things that shouldn't have happened. How many unknowns using a flexibility method? 3, did you say? 3 is correct. One possible way of doing it would be to take off that bottom support, thereby turning it into a bent cantilever, putting the real loads on the structure, letting it bend however it wants to, and counting the fact that it moved down, unfortunately, it moved to the left, unfortunately, and it rotated, unfortunately. This would be delta in the number 1 direction. This would be delta in the number 2 direction. And I think a better name for that than theta and getting mixed up, that's a delta in the number 3 direction. And you'd come back and you'd put unit loads on the structure to form a solution that would get this thing back up to here, properly positioned right and left, properly positioned up and down, and properly oriented in the vertical direction, because it's supposed to come right out of the floor. Another possible released structure could look like that. You'd put the real load on the structure. You'd find that it distorts like this. You'd find that it doesn't move to the left and to the right. You'd find it unfortunately moved down, and you'd find it unfortunately rotates. And again, there's 3 unknowns there. All right, how many unknowns by stiffness method? Booth? 0? No. There's 1. Look at that. There's only 1 unknown. That's the theta at B. In other words, only 1 equation is going to give you all the answers that you need. Whereas in this one here, you had 3 unknowns, and then a whole lot of extra work to put it back to 0. So sometimes these stiffness methods can be really quick. They can give you answers in a hurry. All right, so that's kinematic indeterminacy. Now then, I have got a structure it's a 4-story office building. The boss has assigned me to find the maximum reaction at A, the maximum axial load in column AB. Namely, it wants me to find how big does R sub A get. Now, last week, when I first came on to that job, he had this structure. And he asked, well, no, wait a minute, I don't want that structure. Let me get a simpler structure, because last week I didn't know anything. And he asked me, morning, Getman. Oh, I'm doing great. And he asked me where to put what they call a lane load of any length of your choice on the structure. And it was 3 kips per foot, spread over any length that you like. Where did you put the load on that structure? Left end, right end, left half, right half, left third, whole thing, upside down, backwards? What did you do? Whole thing? I agree. That would cause, he asked me for the largest R sub A max. If you put it over the whole thing, that would give you the maximum reaction at A. Why do I care? Well, I care because I'm getting ready to design this pen. Hunter? You just have an addiction there, don't you? All right. Hunter? Same problem. But now that I want the maximum shear at the middle. It's a simply supported beam. And I want to know, where do you want me to put the load to get the biggest positive maximum shear on that structure? And this is again the load. Max shear. In the middle. Ask your buddy, Mr. O. Where? Just all the way across just the left-hand side? All right, could be. But I'm not smart enough to realize that. So what I'm going to do is I'm going to take the beam home with me, and I'm going to put a unit kink in it. And then I'm going to bring the thing back with me, and I notice that this pin fits nicely in that hole, and I notice that this pin doesn't fit nicely in that hole, and therefore I roll this thing down. This is a 1, and therefore I have generated a thing called opgenorth, a what? What is that thing called? It's an influence line. It's an influence line for what? It's an influence line for shear. It's an influence line for shear where? In the middle of the beam. All right? Now then, having told me where to put the load to get the maximum positive shear, would you like to change where you think we ought to be putting the load? A little louder? A little bit? Well, it's a uniform load. Are you just going to take just a little of it? If you put some here, will you get some answer back out? If you put some here, will you get some added answer? If you put some here, will you get some added answers? So you're supposed to put it all the way across the right-hand half of the beam. Now, I didn't really think there'd be that much trouble getting this. We've already done this before. When the boss said he wants the maximum something, you're supposed to draw an influence line for that item, and that'll tell you where to put the loads. Tell you where to put the wheels, tells you where to put the uniform load, anything else like that. All right, Munson, my boss has now asked me for the maximum positive moment in the center of this beam. What would you do in order to get that answer? That's a good start. I would too. I'd draw the line. You don't ever want to do this on the job site. Now the boss will have a fit. Take it home, put a 45-degree kink in it. There's the old pinhole. There's the old pinhole. Here's the old pin. Here's the old pin. This dimension right here is L over 2. This dimension is L over 2. How far is it down here? 1-to-1 ratio. That means it's L over 2. That means that when you get back on the job site, the influence line no longer is connected. So you'll roll this end up L over 2. And that means this point will roll up how much? How much? L over 2? No. See, this point's out here L, and this guy's only out half as much. L over 4 is correct. And therefore, your influence line looks like this. And it has a peak of L over 4. And now then, you'll take the load that you were given, and where will you put it? Here's a volunteer. You put it all the way across. That's correct. Here's how you find the maximum moment in the middle. You will multiply that area times that area plus that area times that area. You use your volume integrals. Yes, sir. I'm sorry, are you talking about this number here? Okay, see, this is a 45-degree angle, and you were out here at L over 2 when you did the ugly thing to the beam and bent it at a 45-degree angle. So you traveled L over 2 over here, and so it's L over 2 down. All right, now maybe you just joshing me. Well, that's okay. Better here than on an exam. My whole point for going back and doing stuff that you're supposed to already know and be good at, Hunter, is so that I could quickly find out what to do with this one. This is a building with people in it. I don't know where the people will go. Some may be on the roof, some may be on the first floor. But I'll tell you this, if the boss wants to know the biggest reaction that's possible, I'm going to have to draw an influence line for this problem. Let me go back to the beam. If the boss had this same 3 kip per foot spread over any distance that you like, what does the influence line look like for the reaction at A? Zwirneman? That's all you do. You disconnect it on the left and you raise it up 1 unit. That's the influence line for the reaction at A. And what it does is it tells you where to put the uniform load. It tells you to put the uniform load across the whole thing. The final purpose of all of this review is if the boss has asked you in this building to solve for the maximum reaction at A, and let's say you've got a computer program that'll do a nice job of solving this whole thing, you still have the first problem. Where do you put the people? You draw an influence line for a statically indeterminate structure, just like you draw an influence line for a statically determinate structure. The derivation we did didn't have anything to do with whether it was determinate or indeterminate. Turns out it works on these just as well. So what I'm going to do is I'm going to push this up 1. That'll make this go up 1, 1, 1, 1. And that means this will go like this. Except I don't really think that this thing is going to come in here straight because somebody is cranking on it clockwise pretty badly, and therefore I think what's going to happen is that joint is going to have some rotation. Now, I'll admit those numbers are going to damp out pretty quickly. So whereas this number may be 1, this number here may be only 0.2, and this number right here might be only 0.006. And I think that it's going to rotate like this. Probably going to roll clockwise because you pulled up on it, but you did the same thing on that one, and you did the same thing on that one, and you did the same thing on that one. And I don't care too much about those, but they're there, and they influence, and the deformation of this structure, when you put this unit distortion in the reaction, they tell you where to put the load. So if I said, I need you to go out there on the 1, 2, 3 on the roof and put people, where would you put people to get the maximum positive reaction at A? Right next to A, you'd put the people here, and where else? From there to there, because it looks like that's going above the line. And you'd put load here, And putting these people here probably wouldn't change the answer much, but the computer could care less. It doesn't take any time at all. Just put the loads on there. And you'd put the people here, and you'd put the people here, and you'd put the people here, and you'd put the people here. Now, I don't know if you realize what you've done, but you just made it possible to analyze the structure. You say, oh man, I've got slope deflection. I can do anything. I have flexibility methods. I can do anything. Not only that, I got a computer program that means I really don't even have to do slope deflection and flexibility. All I had to do that was so I wasn't ignorant and was going to kill somebody because I don't know how the program works. And that's true, but not slope deflection and not flexibility methods and not computer programs. They don't know where to put the loads. Now then I can tell you where to put the load.
So you put it in the areas of positive?
Anywhere this was up and up, that's where I put the load to cause a positive reaction at A, yes.
So you have to be able to guess the shape?
I just did. Now you say, well, yeah, but you're old and you've been doing this a lot of years. It's not that hard. All I did was I moved that up. And first I did nothing but move the points up. And then by moving them up and having this one not go with me, I kind of realized that joint's probably going to roll a little bit. And whether I drew it a straight line or whether I drew it a curved line is not going to really change my opinion of where to put the load. But you can kind of feel how these things distort. You'll get good at it. Yes, sir.
Why can't computers make influence lines?
Oh, they can. They can make influence lines. And you... Well, that's true, but you also got to know what to do back one step. For example, I could put this structure into the computer and I could give it a unit distortion at A. He wouldn't know why. He would just think the soil had a swelling to it because it got wet and move this point up. And he would tell you, he would give you the influence line for the reaction at A. Then you would come back and look at his output and tell him where to put the load. Now, if you say, well, there's a computer program out there somewhere that I don't have to do anything, I just push the button? Yeah, but they usually don't let newbies get near it. That's what happened at the Kemper Arena in Missouri City, Kansas City. I don't remember which side of the line it was on. Somebody didn't really know what he was doing, and he put in the snow loads, and they were off by a factor of 10. And lo and behold, the first time it really snowed, down it came. It's a mere $1 million. Plus a few people didn't get killed, fortunately, because there's a lot of seats in there, so they just kind of got crunched between the seats. But there's a price to pay for using these things. One of them is you got to kind of know what's going on. Here's the structure. Reaction at B. Draw me the influence line to determine the maximum possible reaction that ever can occur at B, regardless of which rooms fill up. So I'd move this point up, I'd move that point up, I'd move it up, I'd move it up, I'd move it up. And then I would come over here and say it probably looks a little bit like this. See, I'm coming out 90 degrees and coming in 90 degrees. Here I'm coming out 90 degrees and I'm coming in vertically. Influence line for the reaction at B. Where do I put the loads? I put the loads across here. I put the loads across here, put the loads across here, put the loads across here.
So those are the influence lines?
This is the influence line for the reaction at B.
Oh, yeah. The deflections are the influence.
The deflections turn into the influence line. That's correct. All right. Now the boss has assigned me other people are doing other things as we speak. To find the largest shear in the middle of this beam. So what I would do is I would take the beam home, I would put a unit kink in it, I would realize that this no longer fits in here, and therefore I would pull this down to here. And there's my influence line for the shear at this point on this beam so far. You'll notice that I pulled it down and I brought it in horizontally and I brought it in horizontally. I don't think that's probably what's going to happen, because when you pull this thing down and make it go in horizontal, he's going to crank this way on the joint. And therefore I think that joint is going to roll. And I think that joint's going to roll. And I think this one's going to look like this. And I think this one's going to look like this. And there's my influence line. Which one? I missed this one here. Thank you. And therefore, I would tell the analyst when he came to me and he says, where should I be putting the load? I said, well, what kind of load is it? He says, well, first it's a dead load. Where would I have him put the dead load? It is so quiet. Dead load goes everywhere, always. You don't get your choice of where to put the weight of the slab. You don't get your choice of where to put the weight of the carpet. Though that's dead load. That goes everywhere. The only thing you have a choice in any of these cases, is where to put the live load. To get the maximum shear, positive, I would put the load on this half of the room. You say, what do you think the chance of only half the room being loaded up? I say, very good. Over here is the dancing bear, but he lost his muzzle. And all the people are now over here. And I'd put the people 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 here. and here. And I wouldn't put them on that side. And I think that's all of them. Yes, sir.
Why did it only get a kink in one of the beams?
Because the guy asked me for the shear in the middle of this beam, the maximum shear. And you say, well, why did he ask you for the maximum shear in the middle? Because, you know, there is a shear in the middle, and he wants to know how big it is so he can make the web of the beam thick enough to do the job. And you say, good Lord, there's 30 beams in there. You're going to tell me they do this for this one, and this one, and this one, and this one, and this one? Yes, they do. By the hour. Not a problem, by the hour. All right? Yes, sir.
Going back to the reaction order,
All right, hang on. Which flavor would you like, A or B?
either one, the columns.
There you go.
The deal I'm having a problem with is you get like the sinusoidal thing in each bar instead of just like once per joint. Why is
Yeah, well, since we're not going to load it up in there, I probably wouldn't worry too much what the shape was. But you did push this whole thing up. For instance, if it was really fixed on the left, and if it was really fixed on the right, and you move that up like this, it would come back in horizontally, and it would come back in horizontally. But as you see how that curvature of that beam is really going to do a number on that joint and try and make it roll this way. In other words, if you lift up on this part of a stick, the ends want to roll along with it. And that's why I took this joint and I rolled it clockwise. Now that meant that this is a starting and this is a starting. Then I just kind of followed it on until it got to here, kept a 90 degree in there and followed it on. Took this one here and followed it. But this guy also had the same problem. He rolled that joint clockwise. So coming out of the top goes this way, coming out of the bottom of that one goes that way, and I still got to get these two connected together there. If that's the little wiggle you're talking about. Now, this still works even on this, on the side. If you said, where should you put the wind? Well, you ought to put the wind in here, and you ought to put the wind in here, and you ought to put the wind in here, and about now you say, okay, well, that's nonsense. Well, you're right. People, I can put them in the rooms I want to, and it's not impossible, although perhaps not very likely, that they'll really be loaded like we have shown. The wind, there's nothing I can do about that. The wind's going to press on the whole thing, or it's not going to press on any of it. And so probably when we're working out the maximum reaction, I'd run it without the wind on a clear day, and then I'd put the wind on it and I'd see what it gives me. All right, that was shear at the middle of GH. Here is the moment at or to the left of H. Who told me to do this? Raise your hand. Munson. This is point H. This one here. And I want to know an influence line for the maximum positive moment at H. What would you have me do? Just a little to the left of H. In other words, I got to ask you for the moment on the left or the right or above or below. Exactly, it's what you would do. You would come in here and you would take this thing out of the structure and you would put a 45-degree kink in it, just like that. And then you would come in here and you would say, all right, this thing used to fit in a little socket over on the left-hand side, and it used to fit in a little socket over in the right-hand side. And I can tell you right now, this thing's going to be the very devil to get in that little socket. And so what you're going to have to do is you're going to have to crank on this piece of steel like crazy in order to get this thing so it'll fit in the socket. And that's going to make, let me show you the one below it where I've already done the job. It's going to mean this little piece of steel is going to come out straight. It means that it is kinked 45 degrees counterclockwise, 45 degrees counterclockwise, and here it is like this. And I say, well, that's no better than it was before. You say, well, wait, I'm getting there. And then you would come in and you would put it in there. But these joints, they're not going to put up with that. In other words, this thing is going to be cranking clockwise on this joint like crazy. Clockwise. And therefore, I'm going to show you a clockwise rotation of joint H. I'm going to show you that downward distortion. I'm going to show it coming straight in. You're not going to believe me because that's bending clockwise on this joint, and therefore I will put it so that it is clockwise. This thing is clockwise. This one, then I'll follow it along. This one, I'll follow it along. This one, I'll follow it along. This, I'll follow it along. This, I'll follow it along. Got a problem here. I don't know who's going to win that battle. In other words, this guy here is cranking clockwise on the joint, counterclockwise, and this guy's cranking clockwise on the joint. In other words, for it to be bent this way, it has to be doing that to the joint. For this one to be bent this way, it must be going the other way. For all I know, those two may get together and just not do anything. And probably that's just about as good a guess as any. These are pretty easy. These are pretty easy. I don't know what I'd do over there on the left-hand side. I'm not sure I'd worry too much about it. All I'm looking for is a qualitative idea as to how much these things deform and where to put the loads. So to get the maximum positive moment just to the left of H, I would put some load in this span. I would put some load in this span. I'd put some load in this span. I'd put some load in this span. I would probably, I don't know what I'd do in here. Probably wouldn't put any load in there. It might be that it, even if it comes out straight, it's going to be zero. So, and that's negative. I sure don't want load in here. And in here. That's where I'd put the loads. So influence lines work for statically indeterminate structures, just like they do for a statically determinate structure. Now those are, going to take a little thought. Let me do an easier one that's pretty obvious. Barbara. Barbara, where would you put the load between which spans, or on which spans, to get the maximum reaction at C? Maximum positive reaction at C. Where would I put the loads? All right, any others? In other words, you're saying you'd put them across here? All right, let me show you what I think the influence line looks like. Would you like to change your guess? From B to D is correct. This is for max C vertical. Max R sub C. You put the load in those two spans.
Are we doing any quantitative?
You can't really get them qualitative. You quantitative. You can get where to put the loads, and that's really all you care. But can you go ahead and find the answers without using a computer program or without using statically indeterminate analysis? No, you can't. But at least you know where to put the loads, because otherwise you just got a structure. You don't know where to put the loads. You might put some here, then put some there, and put some there, and put some there, and then put some there and there, and there and there, and there and there, and there, there, and hope you run across there. Now I know where to put the loads. All right. Now then, I don't think I can get this on the videos I'm putting out there.